Hello class, this is your instructor, Dr. Mayas. Today's section is 13.4 from the textbook. The topic covered is the equation of motion, the rectangular coordinate system, which we started the discussion already last lecture. So the application will include objects moving in rectilinear motion, like one dimension, or object where the forces are easily decomposed into the Cartesian or rectangular coordinate system. For example, it's easy to use the Cartesian coordinate system for an application which involves a box pushed by a person. Example could be, or question could be, what is the speed or the acceleration or the distance that it takes this box to move from one location to another using this force, which is external force, which is acting at an angle. Another example where you can find or use the rectangular coordinate system is the object with a drag force. This is a rectilinear motion. And you could be asked find or calculate the velocity magnitude after or at a certain instant. Now, following our discussion, we said that a rectangular coordinate system using the Cartesian coordinate, where we have to identify the axis, the positive x and y, and it's not always necessary to be vertical and horizontal. It could be also oriented different ways. But let's say this is my coordinate system, a fixed reference frame, and suppose that we have an object, a particle that has a mass, and this mass has different forces acting on it, from F1 to F2 to many of them, Fn, and each one has, as we mentioned, a direction. This is called the free body diagram, and this is equivalent to the inertia, where the inertia or the acceleration is pointing in the direction of the resultant force. In the other way, to say that if I have summation of forces acting on an object is equal to summation of forces decomposed in I plus summation of forces decomposed in Y, and that is equal to the inertia, ma, or I can write it as maxi plus ayj. So this is acceleration in two directions, x and y. So that's the topic of today. Let's take a couple of examples and dig into details. So we have here an example of a box being pulled by a motor using a cable that's always in tension. What it says is that the motor exerts an external force through that tension with a constant acceleration, so it's reaching a steady state and it's pulling that box at a constant acceleration. So this is one piece of information we need to keep in mind. The box weight is 20 kilogram. The distance traveled, or this box moves 6 meters in 3 seconds starting from the rest position, and this surface between the box and the inclined surface is rough and has a kinetic coefficient equal or dynamic coefficient friction equal to 0.3, and we want to find the tension developed in the cable. So let's summarize this problem example. So we have an inclined surface the angle is given by 30 degree. There is a motor that is pulling a box, and we are given the following. Given the weight to be in, this is all in SI unit system 20, given the coefficient of dynamic, or the dynamic friction coefficient, equal to 0.3, and it doesn't have a unit. We're also given that initially this box at time equal to 0, initially, which is has a 0 velocity, starts from the rest position, that is given. It says that the object travel a distance, so also initially the position we can assume it to be 0, and we can say that within 3 or how many seconds, 6 or 3 seconds, within 3 seconds this travel by 6 meters. So this is all given. So 1, 2, 3, 4, and 5. Anything else? Yes. Most importantly is that the acceleration is a constant. Which acceleration? Well, the acceleration, we have to decide, is it acceleration along the surface, inclined surface. So it's a good time now to choose a coordinate system. So we mentioned that a coordinate system or reference frame should be in such a way to ease the decomposition of the forces, and for inclined surfaces always is good to use a rotated coordinate system. So I'm gonna use this positive y to the right, to the upward I mean, and this is positive x, and the direction of motion, because this is winding in this direction, I expect this to go up. This is the motion, right? So this is just illustration. So I'm looking at x is a constant because this is the motion in the direction of x. There's no motion in y, so also we can say that ay equal to 0. Alright, so this is a summary of the problem. Now let's take a look at what's required. Required is find tension, cable tension. So to know what does that mean, we need to put together the free body diagram and then see what that means. So first of all, I'm gonna redraw that. Initially this is the box, and I chose that this is my y and this is my x, and then within a distance, call it s distance, it travel after 3 seconds to a new location, and this location is right here. Okay, this is pulled by the motor cable T. This is the tension we want to find. The motion is in that direction. This is the motion. Definitely we have a friction opposite to the direction of motion. Also we have a weight, so I'm gonna draw, this is the weight, equal mg, pointing down. This is the gravitation, and also I have reaction, normal, orthogonal to the surface, so this is orthogonal. And let's see, anything else? It's look like this is all what we have. Okay, so so we have chosen a reference frame, we put the free body diagram. Now this is equivalent to the kinetic diagram, where we have max and we have MAY. This is definitely 0 because it's not going anywhere. Not going anywhere. Okay. Now what's next is apply. So okay, so this is like step 1, step 2, step 3 is apply Newton's law. Actually, before I'm gonna do it logically and tell you what is missing and then work on the missing. So when you apply the Newton law, which can be broken down into summation of forces in X equal to the MAX and summation of forces in Y equal to the MAY. Summation of forces in X, well, we have to break it down. So I'm going to start with summation of forces in X equal to 0. I'm sorry, equal to MAX. And then what do we get? Okay, so I need to resolve. So we have a T positive in the direction of X, right? Minus the component of the weight in the X. So it's going to be in this direction, the component. It's going to be mg sine 30. So mg sine theta, let's be general, and then we'll plug in numbers. Also we have a friction minus friction, opposite direction of motion, and this is equal to mass AX. Also in Y, I think we started an example like that last lecture, but we haven't really talked about, plugging in numbers. And the difference is this does have an external force, which is T. And the reason Ty it appears because I'm only looking at the block. So my free body diagram here, just to go back, my free body diagram include anything within this control volume. So this becomes an external force, just for clarity. Alright, so what else? Okay, MAY equal to, this is equal to 0, which is MAY, and the components in Y, N minus mg cosine theta, right? And this is it. Great. Now, because this object is moving, the friction is equal to the coefficient, or the coefficient constant of dynamic friction, μk, multiplied by the reaction force. And we don't know the reaction force, but we know this value, and I think we have it here, 0.3. Alright, so we have one equation, two equation. In fact, I can plug this here and then make it 3 equations. So let me summarize and plug in numbers. So we have an unknown T minus the weight is 20. I'm just plugging in this equation, multiplied by 9.81 and multiplied by the sine 30. I'm here, minus μk, it's a 0.3, and is unknown, and this is the FR, equal to m, which is 20, multiplied by the acceleration AX, which is unknown. So we have, this is unknown, and this is still unknown, and we have another one is unknown. Call it equation 1. Let me plug into that equation, which is n, which is unknown, minus 20, 9.81 cosine 30, equal to 0. So from here, what we get? We get n equal to 20. I'm not gonna simplify that. I'm just gonna give it this as is. So in here we calculated the reaction force N. Okay, so equation 1 prime becomes T minus 20 9.81 sine 30 minus 0.3. Now I'm going to substitute this here, which is 20 9.81 cosine 30, right, equal to 20 AX. Well, this is what I did is I substitute this over here. So this is the only equation now we have. After substitution, these three into one. So this is the final one we have. So this is called 2 prime. But still, this has two unknown. So I need information. So I am asked to calculate the tension. I need to calculate the acceleration. Well, one thing I know about the acceleration is that it's constant, and also what's given to me is the following information. It says it starts from initial position of 0 position at initial velocity of 0, and it takes 3 seconds until it reaches a distance of 6 meters. So this is useful information, because knowing that this object is moving at or under a constant acceleration enables me to use the equation of motion with a constant acceleration. And as you remember, recall from chapter 12 that object under constant acceleration, there are the famous three equations, right? One of them, it says distance at any time equal to the initial distance plus the initial velocity. This initial multiplied by the time elapsed plus half the acceleration t. And since we are talking about the acceleration in x and the distance in x, so this is what we have. Now I'm giving t, I'm giving the initial position and the distance and the time, so I can calculate ax. So simply let's do that. So it travels 6 meters with initial velocity of 0 and unknown acceleration, but that takes time of 3 square, right? So from here we can say, we can calculate the acceleration in x equal 1.33 meter per second square. Okay, so now I know ax, I can plug it back. Therefore, I'm gonna use this, therefore use equation 2 prime, or insert ax in 2 prime, and that one, and then t becomes, after you substitute, it will become 176 Newton. So that's how we calculated the tension. So I took this number, I plug it in here, and then I calculate t. Okay, so that's what give me the total tension. We'll take another example. Alright, so it says here, if the cable has a tension of 3, so this cable all the way has a tension of 3 Newton, determine the acceleration of block B, how much this accelerates. Okay, I mean, there are different scenarios, but let's say this is accelerating, meaning that the weight of block B is sufficient to move block A. Especially we have here some friction, so because of the friction this might not really or not necessarily moving the A, and we will verify that. Okay, so so let's dig into that problem. So I'm gonna use my note. So we're trying to answer two questions. Does really this block move? And if it's moving, what is the acceleration of block B? Okay, I know there's answers there. There's no none of the above, but let's treat that as what's gonna happen. So I have a block A, has a weight. I have a pulley, frictionless pulley. This pulley is supporting another, or it's going around. The rope or cable is going around another pulley that holds block B. This has a weight of 4 kilogram. This has a weight of 10 kilogram. The surface is rough. There's no contact here, so the only thing is happening if this is about to go down, if this is the motion assumed, and that's the only motion we could have because the tension will only pull this to the right, therefore there should be some friction here. And nothing said about the coefficient friction, the static coefficient friction. So this problem is ill-defined as is, but let's work it in a backward way. Okay, the question is given here mu k equal to 0.4. I should have also another value in mu s, but it's not known. So this is why I'm saying this problem is ill-defined. For our purpose, I'm gonna give it a number, and let's say it's a 0.3. Okay, so because we know, sorry, 0.5. Okay, 0.5, or the static coefficient of friction is larger than dynamic one. Okay. Okay. All right. Now we want to find the tension. What's given to us is, I'm sorry, the tension is already given to us. It says what's the acceleration of block B. So I need to draw the free body diagram of block B. This block B has two tensions here, which are known, and I have definitely a weight which is equal to 4 by 9.81. This is 3 Newton and 3 Newton, right? Newton, Newton, Newton. And because the tension is already given to us to be 3 Newton, it's kind of telling us the net forces. In fact, if I want to sum the net forces, it will be not zero. Actually, the net forces will be in the favor of downward. So if I choose this to be my positive, right, then, and I sum all the forces for this block about the y direction, then what do I get? I get 4 by 9.81, right, minus 3 plus 3, 6. So definitely this is non-zero, and this is going to be equal to MAY, and M is our 4, right? So this is 4. So therefore, because this is net is in the downward direction, we expect that this weight, it will be sufficient to bring us down. So let's calculate for now the acceleration of block B. Okay, so acceleration of block B is going to be equal to 4 by 9.81 minus 6 over 4, and that is going to be equal to 8.31 meter per second, and it's downward. Okay, so we figure this out, but we want to verify one thing. In fact, and I'm gonna remove that for now. I wanna see what's really happening to the block A. So block A has a tension, has a friction, right? R, which is equal to mu n. There's an n here and there is a weight here. So if I apply, this is, we said this is going to be my y. I can say this is going to be my x, right? Summation of forces in y equal to 0 for this block. So therefore, n equal to the mass of block A multiplied by g. So this is n equal to 10 by 9.81. So n of A, right, of A is going to be equal to 9.81 Newton. Okay, and then I apply, let me do it here, summation of forces in y direction. So we did this y in the x direction equal, so this is the x, is a t minus the friction equal to the mass of block A multiplied by what? By the acceleration of block A in the x direction. Okay, the tension is already given to us. The friction, we're not really sure what's the friction, so if I were to calculate the friction, I should be able to do that, but let's do that here. So this is 3 minus friction, I'm going to calculate the friction here, equal to, this is 10 multiplied by AX. Alright, now what is the relation between the acceleration of A and acceleration of B? Well, we know there is a relationship, and that relationship is from the geometry. So if I use this as a datum to calculate the position of SA, the position of this block, and use this datum to calculate the position of block B, then the total length from the dependent motion, what do I say? That to the length of the cable equal this length, this portion, that portion, plus that portion, plus the redundant one, right? So plus SA, all of them referenced the way I'm showing there, equal to some length or some constant. So therefore, the acceleration of A, if I take in the second derivative, equal to negative acceleration of B multiplied by 2, and this means that the acceleration of A, this block, which is again the x1, because there's nothing else, is equal to what? Equal to negative acceleration of B, which is in the y direction, and that was calculated already 8.31. So 2 by 8.31, right? And the negative mean it's, as this is going downward, this is going to be going opposite of that direction, so it's going to the right. So this means it's a 16.62 meter per second square and going to that direction. So that's what it means. So now going back to our equation, call it equation 1 or star, substitute in equation star. What do we get? We get 3 minus Fr equal to 10, 16.62. I use positive because this is positive to the right. So Fr equal to 10, 16.62 minus 3, all negative, right? So it's 166. And this has become 362 negative Fr. And okay. Okay, so as you can see here, the friction force I got is a negative 163.6, which is impossible for many reasons. First of all, the negative means is opposite to the direction was assumed, which is over here. I assumed it here, and this is because the motion, if this is going to go down, the motion of A should be to the right, and therefore the friction must be to the left. So this is the correct notation. Now what I got when I analyzed based on the given information is that the friction is the opposite, meaning that this object wouldn't develop that tension without having additional force pushing the object A to the right, which is, this is the mathematical solution, which is physically is impossible. Therefore, going back to the problem, which is in the presentation file, I just want to tell you that not all the problems are stipulated right. So this is from a textbook that we are using in the class, and so the problem itself here is wrong. And the way I was checking it is that for this really to move in a given tension 3, there should be different settings, right? And the tension will not be 3 in any circumstances. Therefore, I know we calculated, and we're showing here that the answer is D, but you know, D if and only if we are not given any information like about the 10. So if we don't know this, then we can say, yeah, it should be D. But if we are giving that mass of A is 10, then there's a big question mark about, you know, the information provided. So therefore, anyway, so the answer is D, but I wanted to remove the information about the weight of A, because that will make the problem not working. Alright, we'll take another one. Okay, so this problem is, probably you remember that from maybe static. I have an inclined surface at an angle theta. I have a box that or a particle that has a mass m. This surface does have friction mu s, and also dynamic friction mu k, right? Now the question is, first question, I mean, this problem has twofold. At what angle the object start sliding downward? Okay. Second, what is the speed of the particle or block or box after 3 seconds with angle theta equal to 70. Okay, and mu s equal 0.3 and mu k equal to 0.2. Assume object is initially at rest position. Okay, so let's look at the first question, which is a little bit general. So we have a box, a weight, the free body diagram. Well, this will attempt to slide downward, so the motion is in this direction. So therefore we have here Fr, which is equal to the mu s n. Now I put it at mu s because I'm interested to find the minimum angle at which the this object will start moving. So when theta is 0, we know this is not moving, and as theta is increasing, the component of the weight in this direction, the horizontal direction, will increase, and as a result of that, it will overcome the friction or the friction component and make this to slide. We have also the reaction force N. Okay, and my Cartesian coordinate system, this is y positive and this is going to be my x positive. Okay, and now this becomes so summation of forces in x, this is in x, is equal to what? Is going to be equal to mu s m. I didn't put mu k because I want to find the minimum angle at which this block will start moving. So this object is not moving anyway. So definitely the summation of forces assumed here is going to be equal to inertia, equal to the inertia, right? Oops. And the inertia MAY, this is equal to 0, and MAX equal to 0 because we said the object is staying still. What's the minimum angle? Sliding downward, so which means that it's not sliding at that angle unless, okay, unless than that angle value. So this is mu s n f, which is that one, minus the component of the weight in the x direction, so this is sine theta. And also we have another relation, which is n minus mg cosine theta. Now this is definitely 0 and this is 0 because they are not moving. So what do we get from the second one? From the second one we get n equal to the mg cosine theta, and from this first one we get that m, and I'm going to substitute mg, right? Mg cosine theta minus mg sine theta. So this is, just to be a little bit more organized, then substitute this in 1 and we get this, okay, and this is equal to 0. Okay, so I want to find the requirement. Now looking at this problem, it's look like this, that will cancel, so I'm going to end up with mu s cosine theta minus sine theta equal to 0, or mu s equal to sine theta over cosine theta equal to tan theta. So that's, if you remember that from static, that's the relationship between the mu s and tan theta, the the minimum angle required to move this object, which is in fact tell us a lot, because if I want to really find experimentally the value of the static coefficient of friction, I can conduct an experiment and monitor the theta, and at this angle when the object starts to moving, I can record that and calculate the tan angle to get the mu s. Okay, great. So that's the relationship. Now for the second one, we have more information given to us. What do we get? So it does say that we have an angle, and that angle is the following. It does have an angle of 60 or 7. I'm sorry, it's 70, right? And I want to find the velocity. It was over here. Now I don't know yet if this is gonna move or not, so I have to make a check on that. So before the question is given that mu s is equal to 0.3 and mu k equal to 0.2. For this object to slide, the following has to be satisfied. So I want to calculate mu s. So if the theta, I want to calculate theta. If theta, tan theta or tan is greater than mu s, then it will slide. Okay, so for this to slide, I'm gonna calculate tan 70 degree, right? Or let me make it a little bit different. I want to calculate theta that, okay, so if mu s is equal to 0.3, this is tan theta, right? Meaning that at what angle this will start slide, given that the surface is roughness is having static coefficient of friction of 0.3. So this will give us that theta, and I'm gonna do this calculation in the side. So according to these numbers, the minimum angle for this object to slide with the static coefficient of friction 0.3 is 16.7. So since the angle that I'm studying is 70, which is far exceed the minimum 16.7, therefore this will definitely slide with a dynamic coefficient of friction of 0.2. So yes, it will slide. Now it will slide, meaning that the problem now is clear. Gonna slide downward. This is your motion, and that's gonna be your mu kn, not mu s. This is because it's sliding, and I have here a w, and here is a 70, right? And now I just apply the same equation I did there, but the difference is we don't have here 0, we have a value. So summation of x using the same coordinate system equal to m of the particle ax equal to mu kn minus mg cosine theta. Which theta? Not that theta, but the 70. This is the problem we are trying to solve, right? And this second one, summation of forces, nothing is happening in the upward direction. Okay, now which means n simply is equal, let me calculate that now. mg, m is, I assumed it to be equal to, I don't remember, did I give a mass? Well, I did not give a mass, so let's say the mass is, let's say m equal to 2 kilogram, So this was not given initial, so let's define it now. So this is equal to 2 by 9.81 by sine 70. Okay, this is the first thing. And then I'll substitute that over here and calculate the AX. So this is 2 by AX equal 0.2 by the N minus M, which is 2 by 9.81 by cosine 70, right? So AX can be calculated. Alright, so after calculating this equation, the AX is equal negative 3.026. So what's negative means? Means it's opposite to the reference X which we are using. So it's not going to upward, it's going downward. So that's what it means. So AX equal 3 meters per second and it's going downward. Okay. Now what we will do later is calculate the velocity. So we want to calculate the velocity of the object after a certain time, which is, I think we said, starting from rest position after 3 seconds. So what's going to happen after 3 seconds? So what we expect, because of the acceleration, is that this object will start getting some momentum because of the acceleration. So this is its acceleration, x equal to 3, starting from the rest position, s equal to 0, right? Velocity equal to 0. How much is going to be after 3 seconds when it reach downward, right? After 3 seconds. So what we will do is, well, since there's no other forces acting on this object except the weight and the friction, and these are constant, therefore we expect this acceleration to be always constant, 3. And for that you can use the equation of motion. The equation of motion with a constant acceleration. Now what we're looking for is how to calculate the velocity, right, after 3 seconds. So we're gonna look back and look at the equation of motion. So at constant, with AX equal to 3 and this is constant, use V at any time equal V initial, which means V at time equal to 0, plus the acceleration, which is constant, multiplied by the time elapsed, right? So what does it mean? So V at time equal to 3 seconds, initial is 0 plus 3 multiplied by 3 seconds. That's what we were asking. So this is equal to 9 meters per second. So that's the answer. So with this we finish the rectangular analysis. The next lecture will be normal and tangential and cylindrical. With this we finish the section 13.4.